Paragraph 1. Imagine looking up at the sky and witnessing a dawn that takes up half the horizon. NASA has recently released images of a never-before-seen phenomenon involving the star Betelgeuse, which erupted violently, ejecting a significant portion of its surface mass. This event, known as a surface mass ejection, SME, was recorded to have released 400 billion times more mass than a typical solar flare from our own Sunday. Scientists described it as watching cosmic evolution unfold in real time, with Betelgeuse shedding massive parts of its physical structure. This unprecedented outburst from the red supergiant has left astronomers questioning what caused the explosion and what effects it might have on our understanding of the universe. Paragraph 2. Betelgeuse, a well-known star located in the constellation Orion, has long been an object of fascination for astronomers. It is one of the largest and brightest stars visible in the night sky, located in the upper right shoulder of Orion the Hunter. The star is easily recognizable due to its bright red hue and is often used to demonstrate to skeptics that stars indeed come in a variety of colors. Known as Alpha Orionis, Betelgeuse is the second brightest star in its constellation after the blue supergiant Rigel, even though Rigel appears more luminous. Despite its brilliance, Betelgeuse holds the Alpha designation because of its size and distinctive red color, making it one of the most recognizable stars in the night sky. Paragraph 3. Betelgeuse is the seventh brightest star visible from most of North America, Europe, and Canada, and it ranks as the 10th brightest star overall. Its proximity to Earth, while not precisely known, is estimated to be between 430 and 724 light-years away, making it the closest red supergiant of its kind. If Betelgeuse were to replace our Sun, it would extend beyond the asteroid belt and even past Jupiter, consuming planets like Mercury, Venus, Earth, and Mars due to its enormous size. It is about 700 times larger than the Sun, with a radius nearly 1,200 times that of the Sun and a luminosity 126,000 times greater. Betelgeuse shines with a surface temperature of about 3,600 Kelvin, making it cooler than the Sun. Only 13.3% of its radiant energy is visible light. If human eyes could see all light frequencies, Betelgeuse would appear brighter than Sirius, the brightest star in our sky. Paragraph 4. This red supergiant is surrounded by a cloud of material roughly 30 astronomical units wide, about 30 times the distance from the Sun to Neptune. Like our Sun, which ejects small amounts of mass during solar flares in a process known as coronal mass ejections, CMEs, Betelgeuse has experienced a far more dramatic version of this event. The SME it experienced in 2019 expelled a massive amount of material into space, forming a large cloud of dust that temporarily dimmed the star when viewed from Earth. This cloud of debris was so dense that it altered Betelgeuse's usual brightness and disrupted its typical pulsation pattern, which had been consistent for over 200 years. Paragraph 5. What makes Betelgeuse's SME even more extraordinary is its scale. The amount of mass ejected was 400 billion times greater than that of a normal solar CME, which caused the star to wobble and shake like a bowl of gelatin. According to NASA scientists, including astronomer Andrea Dupree, this outburst may have been triggered by the star's internal convection cells falling out of sync, causing its surface or photosphere to struggle to reconstitute itself. This dramatic event has given scientists a unique opportunity to study the life cycle of stars, especially red supergiants like Betelgeuse, which are nearing the end of their lives. Paragraph 6. Most stars, including Betelgeuse, are powered by nuclear fusion, a process where hydrogen atoms fuse to form helium, releasing tremendous energy. As stars age, they exhaust their hydrogen fuel and begin fusing heavier elements like helium, carbon, and eventually iron. When a star starts fusing iron, it absorbs energy rather than releasing it, leading to a collapse under its own gravity and eventually triggering a supernova explosion. Stars like Betelgeuse undergo dramatic color changes as they evolve. Young stars are typically blue and hot, while older stars like Betelgeuse are cooler and red. Paragraph 7. Historical records suggest that Betelgeuse may have once been a yellow supergiant before cooling down and becoming the red supergiant we see today. By studying the mass ejection event on Betelgeuse, astronomers hope to gain a deeper understanding of how red supergiants lose mass in the final stages of their life cycle before exploding as supernovae. As one astronomer noted, "We've never witnessed a surface mass ejection of this magnitude before." This completely new phenomenon allows scientists to observe and learn about stellar evolution in real time. Paragraph 8. However, despite the wealth of data provided by Hubble and other telescopes, it remains unclear whether this outburst signals Betelgeuse's impending supernova. The event has been so unexpected that NASA and astronomers worldwide are left with more questions than answers about this massive star. Betelgeuse may not explode as soon as we think. Infinite time is long, and while red supergiants like Betelgeuse die quickly on a cosmic scale, NASA estimates that Betelgeuse might not go supernova for another 100,000 years. Paragraph 9. Betelgeuse has been intensely studied since the 1st century BCE. More recently, a team of researchers led by Sarah Nance investigated the likely timing of supernova explosions in red supergiants like Betelgeuse, aiming to understand how such massive stars behave over time. Nance's team ran simulations using Betelgeuse as a model and compared their results to real-world observations to find out why the star dimmed so dramatically in 2019. Even though it is not expected to explode for 100,000 years, Betelgeuse was expelled from its birthplace in the Orion OB1 association, which includes the stars in Orion's belt. Paragraph 10. The star Betelgeuse has been observed moving through the interstellar medium at more than 1 light-year per year. By mid-February 2020, Betelgeuse had lost over 2/3 of its brightness, dropping from magnitude 0.5 to 1.7 after beginning its rapid dimming in October 2019. By February 17, 2020, the star's brightness had stabilized for about 10 days before it began to brighten again. However, Betelgeuse seemed to have stopped dimming completely just 5 days later, effectively ending the episode on February 24, 2020. No significant changes were detected in the infrared spectrum, suggesting that the recent visual dimming was not related to the anticipated core collapse. Paragraph 11. One study concluded that the dimming was likely caused by a cloud of large-grain circumstellar dust. However, another study using measurements at submillimeter frequencies ruled out the absorption of dust, suggesting instead that the dimming might have been caused by large star spots. Further research showed a dramatic rise in Betelgeuse's brightness between May and August. Betelgeuse is so close to the Sun that it cannot be seen from Earth during certain periods. For instance, in mid-2020 Betelgeuse was in conjunction with the Sun, and by June and July, observations made using NASA's Stereo A satellite showed that the star had faded by 0.5 magnitude since its previous ground-based observation in April. This surprised astronomers because the star's maximum brightness and subsequent dimming were expected to occur around August to September 2020 and April 2021 respectively. Paragraph 12. Betelgeuse's brightness is known to fluctuate unpredictably, making predictions difficult. The 2020 dimming event suggested that a second dimming episode could happen sooner than anticipated. The discovery of a second dust cloud detected in June 2020 pointed to the possibility of a cool patch on Betelgeuse's photosphere being the source of the dust. By August, another independent study confirmed this hypothesis. The dust likely formed from gas that Betelgeuse expelled. A 2022 study using the Hubble Space Telescope indicated that a surface mass ejection, SME, may have created the dust storm. This material, expelled from the star's surface thousands of kilometers away, cooled and condensed into the dust cloud that obscured Betelgeuse from Earth's view. Paragraph 13. The broken photosphere, weighing about 3 times as much as our Moon, was ejected into space, cooled further, and created a cloud of dust that dimmed Betelgeuse from Earth's perspective. The dimming, which began in late 2019 and lasted several months, was noticeable even to backyard observers who saw a significant change in the star's brightness. More strikingly, the supergiant's usual 400-day pulsation cycle seemed to have vanished in recent years. Astronomers have long tracked this cycle by analyzing changes in Betelgeuse's surface movements and brightness fluctuations, and its disruption highlights the extent of the recent disturbances. Paragraph 14. Scientists now have a working theory to explain the disruption. Betelgeuse is slowly but steadily regaining strength, and its photosphere is beginning to recover. However, the star's normal cycle seems to be lost, and its interior is vibrating like a belt that has been damaged. An SME of this scale has never been seen before, and there is still much about this phenomenon that remains unexplained. We may be witnessing this entirely new event firsthand, using tools like the Hubble Space Telescope to observe surface features in real time. Paragraph 15. When will Betelgeuse explode? It is uncertain. It may not happen in our lifetimes, or it could occur tomorrow or 1,000,000 years from now. However, the explosion will not destroy Earth. For a supernova to pose a threat to human life, it would need to be within 50 light-years of Earth. Betelgeuse, located over 10 times farther than that, will instead treat everyone on Earth to a stunning view of a bright star in the night sky when it finally explodes. Paragraph 16. Thanks to Betelgeuse's proximity, astronomers will have an unprecedented opportunity to study a star undergoing a supernova. Although Betelgeuse is currently not visible in the night sky, even if it had already exploded, we would not yet see its light given that the explosion would have occurred more than 500 years ago. Researchers are eager to witness Betelgeuse's epic eruption and subsequent recovery. In the meantime, NASA's James Webb Space Telescope may be able to track the material ejected from Betelgeuse as it travels through space, while the Hubble Space Telescope continues to monitor the star. Paragraph 17. Betelgeuse's recent behavior plays a critical role in advancing our understanding of stellar physics. The sheer scale of its SME challenges current models of stellar behavior and evolution. Traditionally, the mass loss process in red supergiants has been understood as a steady and predictable mechanism. However, Betelgeuse's recent explosive event reveals a more chaotic and turbulent side of these massive stars. Paragraph 18. One particularly intriguing aspect of Betelgeuse's behavior is the potential for such events to serve as precursors to supernovae. The star's unusual mass ejection could provide valuable clues about the final stages of a star's life and the nature of supernova triggers. By studying Betelgeuse, scientists hope to identify the factors that lead to such dramatic stellar changes and refine predictions about supernova occurrences in similar stars. Paragraph 19. In addition to shedding light on Betelgeuse's unique situation, these findings emphasize the intricate connection between a star's internal processes and its observable phenomena. The relationship between the core dynamics and outer layers during massive ejections could offer insights into how other supergiants evolve and eventually explode. This understanding may have broader implications for the study of galaxies and the distribution of elements throughout the universe. Paragraph 20. Betelgeuse's behavior underscores the importance of multi-wavelength observations. While optical telescopes provide critical data, infrared and ultraviolet observations are essential for capturing the full scope of the ejected material and its impact. Instruments like the James Webb Space Telescope and various ground-based observatories play a vital role in piecing together the complete picture of these stellar events.